Hey everyone, yo, it's me Deepak. So today we'll be solving this problem that is named as from from source to target. I need to figure out that what all paths are possible. So let's firstly look into this. And also, it's not just a problem that I'll be solving. Okay, and yeah, that's done. No, we'll be looking at the intuition. And if you understand this problem, so this is the base. This is the classic problem, and based on this, on top of it, there's a lot of problems. Means if you understand the intuition behind it, the brain ignition will be there. So you'll be able to solve any similar kind of problem. I hope you're getting. So look, before digressing from any of those points, let's look at this question that what is asked to us. That is all paths from source to target that I need to uh, 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 figure out. So over here, what is given to us is this. That is, I just have a directed acyclic graph. So here I know that what type of graph I just have over here. So it's the acyclic. So obviously there won't be any cycle. So there's no chance of entering into the loop and looking into the same node again and again. So basically, what does we do for any kind of graph problem in order to implement it? So if you have hands on a multiple problems, if you have solved multiple problems evolving out of the graph, so you'll be knowing this thing that we should keep a visited array in order to figure out that what all nodes have been visited till now. So there's no cycle, so there is no repetitive guide. So obviously we won't be going with the visited array kind of stuff over here, and it's a directed. So obviously, so that is this is the node, and this is another node. So I know that from this, from this node I can go to this node only. I know the direction. It can't be the case that okay from this node I can go to this node. So or there will be a loop, that is a cycle. So that's not the case. So this is the hint that is given to that. It's the directed acyclic graph that is tagged. So there's no repetition. So there's no visited array that would be required. So where we have nodes and number of nodes labeled from 0 to n minus 1. If I does have 5 nodes, so it will be from 0, 1, 2, 3, 4. That is 0 based indexing nodes I does have over here in this case. And I need to find all possible paths from node 0 to node n minus 1. Okay, from node 0 to node n minus 1. I does have node from 0 to n minus 1 only. So that indicates what? That is over here, I does have source. That is the starting node itself, which is over in this case is what? It's 0. And I does have destination as well. That is what? That is the last node. And O in this case is that last node is what? Let's see, that is the n minus 1 O in this case. The last node is that. So I have source and destination. So there won't be multiple destinations. Only one source, one destination. That's it. So that's also it become easier for us to proceed with. So that is given to us, and I need to return them in any order because we'll be looking at this here 0, 1, 2, 3. So it has 4 nodes. So 0 is the source node, that is this, and n minus 1. And is what over in this case? It's 4. So that is n minus 1, that is 3. 3 is the target node. So from 0 to 3, I can go from 0 to 1, 1 to 3, from 0 to 2, 2 to 3. So I can bring it, I can print it in any order. It's not this thing that I should let the compiler the compiler knows that okay, this is the path, one path, and then only this is the path. No, it can be in any order, 0, 2, 3, 0, 1, 3. It doesn't matter. But at the end of the day, what's the uh, important thing over here is that we need to emphasize that we want all the possible paths from source to destination, or in this case. So that's what we want to find. And so the input given is in this kind of format. That is, the graph is given as, that is, graph of I is a list of all nodes you can visit from node I. That is, there is a directed edge from node I to node graph of ij, which indicates what? That is over here what I does have graph. This is the graph which I does have in this case, something like this. Now if I was saying okay, so it's a 2D matrix. I can say it's a list. So I can, if I'll give the index to it, so it's something like this 0, 1, 2, and 3 over in this case, something like this. Okay, it indicates what? Okay, I just have a list of directions from which node to which node I can go. So I just have various list in it, as you can see. So what I just have? I just have list of list over in this case, and in that one element, that is each list determines okay from that index what all outgoing edges I just have. It indicates what? That is, from 0 I can go to 1, from 0 I can go to 2. If you look into this example carefully, so here you can determine that. That is, from 0 I can go to 1, from 0 I can go to 2, from 0 I can go to 1. That is, from 0 there is outward edge to 1, from 0 there is outgoing edge to 2. So from that index, what all outgoing edges are there? That list I will be having. Or in this case, from 1, what all nodes I can go? So from 1, there's outgoing edge to 3. As you can see over here, like this. From 2, what all outgoing edges are there? That's also going to the 3, something like this. And from 3, what all outgoing edges I does have? No, 3 is not pointing to anyone. Okay, it has the in degree 2, and it has the inward edges, but it doesn't have the outward edges over in this case. So this is the input that is given to us. That is a graph over in this case. Cool. So the output is also given to us. That is what? Something like this. As I already let you know that how the output and what is it can be in any order. So I can go to from 0, 1, 2, 3. From 0, I can go to 1, 1, 2, 3. 3 is the destination node, 0 is the source. I has a 4 nodes, so n minus 1 will be 3. So 3 is the target node and 0 is the source node. And from 0 to 2, 2, 2, 3, I can go to something like this as well. So this is the path I need to determine. Okay, one path is this and one path is this. Okay, one, two paths. There are two possible paths that are done. I have found it. Cool, great. Now, that is the thing I need to figure out. Let's figure out how I can do this thing. Okay, is it directed acyclic graph? So I can also implement certain kind of algorithm. The pattern that I can get over is that I just have what? This is what? This is a directed acyclic graph that I just have over here in this case. Directed acyclic graph. So there's a topological sorting. Means I can sort all the nodes. What does this means? That is, if there's a directed acyclic graph and there's an acyclicity, so there won't be any cycle. So obviously that one node will be going to another node. It won't be the case that let's say U is the node and V is the node. From U I can go to V. So from V I won't be able to reach to U. So if it is the case, so there's the it behaves like the undirected only. And topological sort says that if I can represent the graph given to us in such a manner, that is in the linear ordering, such that if there's a, let's say there's a U, there's a V, there's an edge between U and V, and where U comes before V. So this pattern I can apply, but there are various approaches I can go with. I need to do what? Traverse all possible paths. So I can go with BFS, DFS as well. So, but the main idea, the direct approach, the first approach that comes to mind is that DFS, I'll be going depth, that is 0, 1, 3. I found one path. 0, 2, 3. I found another path. I'm doing what? 0, 1, 3. I'm going depth until I'm not able to find my target node. That's what I'm doing in this case. So, and I'm backtracking and I'm figuring out for the next path if there is any. I'm going to 2 and 3. So that's the direct approach that came to my mind. So let's start with that approach. Okay. So what is that? That is, I'll be applying depth first search over here. Not the source node. Why source node? Because that is the starting node. From that only I'll be going forward now. From 1, 2, or whatever the node areas over in this case. So that's the thing I'll be saying. I'll be doing. So if I'll be taking the example over in this case. So what is this? I just have how many nodes over in this case? I have 5 nodes. So the starting will be what? Starting will be obviously 0. And the destination in this case is what? That is n minus 1. And n minus 1 is what? That is 4 in this case. Okay. That means 0 is the source node. 4 is the destination node. That is the target node which I need to face from source to destination. I want to find all the paths. Okay. That's the thing I just have in this case. So I'll be having a list over in this case. Okay. That is this. Input is given as this. Oh yeah, this is the input that is given to us. Great. Now I'll be saying, okay, this is the input. And if I'll be saying doing it this, if I'll figure out at which all outward edges has from which all nodes. So I can say, okay, if I'll write the index for each, that is 0, 1, 2, 3, and 4. Something like this. Cool. This is the thing I have over in this case. Okay. From 0, I can go to 4, I can go to 3, I can go to 1. That is 0 has 3 outward edges. 1, 4, 3. From 1, I can go to 3, I can go to 2, and I can go to 4 as well. That is if I will. So it's saying from 1 I can go to 3 to 4. From 1 I'm able to reach 2, I'm able to reach 3, and I'm not directly able to reach 4. Why I can go? Okay, here is the edge. I can go something like this. Cool, great. From 1 I can go to 4, and from 2 I can go to 3. There is only one outward edge for 2, and from 3 I can go to 4, and from 4 I can go nowhere, even though it has 3 in degree, from 0, from 1, and from 3. But I can go from 4 to anywhere else because that is the last node I has over this. That is the target destination. Okay, that's the thing I can do. Great. So now I will be saying, okay, I want what? I want the path. I want the path for each from okay, I want all the possible paths. Okay, so let's say result I reserve. I want the list of all the paths. List of all the paths. List of list. And path is what? Path can be, oh, in this case, as if you'll see 0 to 4, I can go to from 0 to 4. If you see over here, what all possible paths are there? From 0 to 1, I can go. From 1, I can go to 2. Great. From 2, I can go to 3. From 3, I can go to 4. Done. 0, 1, 2, 3, 4. One path. From 0, I can go to 1. Again. Listen this thing. From 0, I can go to 1. From 1, I can go to 3. From 3, I can go to 4. 2 paths. Now from 0 I can go to 3, from 3 I can go to 4. 3 path I have till now. From 0 I can go to 4. 4 path I have till now. So I can return it in any order. So these all are the paths available over here. And also from 0 I can go to 1, from 1 I can go to 4. This path also. We need to take care for this as well. This edge. Cool. 5 paths I have over in this case. Cool. That I need to identify. Okay. So that means what? Path. Path is what? Path is the list of elements, or I could say the list of nodes I would be requiring. And result will be what? I want to return what? List of path. Okay. I want to return the list of path. This is one path. This is one path. This is another path or something like this. So I want to return the list of all the paths over in this case. So that's the thing I need to do. Okay. If I'll be saying, okay, I'm saying, okay, DFS. I'm writing a DFS. I'm saying, okay, start from the source node and passing the graph what I does have in this case. Graph will be indicating that, okay, from which node I can go to what all nodes. That detailing I will be having in the graph. That will be help me to identify, okay, from 0 I can go to what all nodes. What all are the next possible nodes? Means who all are the neighbors of 0? What all the outgoing is to which all node it points? That's the outward edges. So I'll be passing graph as well. Cool. And I'll be passing uh, path. That's okay. Means here I'm doing what? I'm doing, okay, at a time. I'm saying at a time I'm figuring out one path only. That is depth I'm going. So at a time I'll be figuring out one path, and the moment I reach to the target, I'll be saying, okay, path is done, add it into the result. That's the thing I'll be doing. Okay, so I'll be requiring a result as well in this case in order to add the each path. Okay, I'll be starting from the 0 node. Great. So I'll be saying, okay, from 0 I'll be doing, okay. So now what I'll be doing in the path, currently what node I does have? I does have in the path only 0 till now because I'm starting from the 0 node. Okay, so now I'll check, is this node the target node? That is the 4. No, it's not. No, it's not the target node. Okay, so go and do the DFS for that of DFS again, or in this case, if I'll be saying something like this, oh yeah, I'll be saying, okay, it's not the DFS. Okay, go and do the DFS for what? Oh yeah, I'll be requiring this thing, DFS for its neighbor nodes. What all are the neighbor nodes? 1, 4, 3. Go and do the DFS for all 3 nodes. Okay, go and do the DFS for all the 3 nodes which I does have. I'll be going each one by one because the depth wise I want to go. Okay, so now I'm going with the 1. Okay, and after that I'll be going with the what? That is 3, and then after that I'll be going with the 4. Cool. That's the thing I'll be doing. So over here, this is the thing I does here. Now I'll be saying, okay, is 1 is the destination? That is 4. No, it's not. Okay, so this has to also be in the path. Now again, go and do what? Look for its neighbor. Okay, what all are the neighbors of 3? Oops, 1, because the last node is in this case what? 1. Now who are the neighbor nodes of 1? That is 3 and 2. Okay, so I'll be calling 2 DFS for 1 and 3, for 3 and 2. Okay, now firstly I'll go with the 3. Now is 3 the node which I want? That is 4. No, it's not. So 3 should also be the path. Now I'll go with the neighbor node of 3. Okay, who all are the neighbor of 3? That is 4. Okay, I'll be doing DFS call for that as well. That is 4 in this case. Now I'll be saying, okay, 4. Now I'll be saying, okay, is 4 is the destination node, that is target node, that is 1. I'll be saying, okay, yes, it is. So I'll be adding that as well. Now I'll be, if I know, okay, it's done. Now this path is done. Now I'll be saying what? Okay, in result, add this path. Add the path which I have in this case. That is what in result. What I have over here? I have 0, 1, 3, 4. So I have 3 one path. I found one path over here. Great. I found one path. Now if I'll be doing what? I'll backtrack. Now it's done. I'll go here. Is there anything which I need to go, which I need to look? No, there's nothing because 3 was having only 1. 3 has only 1 outage. Okay, now again backtrack. Is there anything which I need to figure out? Okay, yes, there is one more neighbor of 1. That is 2. You need to look for that as well. Okay, I'll look for that as well. So what I'll be doing? Okay, I'll be saying, okay, who all are the neighbors of 2? In this case, I'll be saying, okay, 2 has neighbor only 3. I'll be going with the 3. 2 has only neighbor 3. But before that, I'll say, okay, is 2 is the one which I looking for. No, it's not. It's not the 4. So that will be in the path. Okay. Now I'll be going for this neighbor node, that is 3 over in this case. I'll be saying, okay, call one more function, DFS call. Over here, the node will be 4, that is the neighbor. I'll be saying, okay, is 4 the one which I'm looking for? Yes, it is. Yes, now it I have found. Now in the result, I just have what? In the result, earlier I was having this path. Now I just have one more path. That is what? That is I just have one more path, that is 0, 1, 2, 4. Great. Now I'll be saying, okay, from this is also done. Now I need to backtrack. Is there anyone which for which I need to do the DFS? It will say no. The 2 was having only one outward edge, is 3. 3 has is the neighbor. There's nothing. So I'll be saying, okay, now I can backtrack. Now 1. Do I need to go further for any of your neighbors? No, there is no neighbor, so it is also done. Now I can backtrack. I will say, okay, 0. Is there any other neighbor that you have? I will be saying, okay, yes, I does have. Great. So call for that. Make a DFS call for that as well. Over there in this case. Great. So I'll make a DFS call for that as well. I'll be saying, okay, 3. Are you the node which I'm looking for? I'll be saying, no, I'm not the 4. So add that node. And is there any neighbor of 3? It'll be saying, yes, I have one neighbor, that is 4. Okay, do the DFS call for that as well. No worries. I'll be doing the DFS call for that as well. Something like this. Great. Now, what I'll be saying, okay, that is done. Now I'll be saying, hey 3, are you the I made the DFS call for 4 over here. From 3, 3 was having the neighbor node 4. From 3 I went to 4. I'll be saying, okay, 4. Are you the 4? That is a target node. I'll be saying, yes, I'm the target node. Okay, add it. Now it is a target node. I reached over here. So now this is also done. So this is also one of the path that I can have. Great. Then so add it into the result. That is what? One more path is what? 0, 3, 4. Great. Now I'll be saying, okay, I'm done. Now you can do the backtracking. Now I will go back from 4 to 3. I'll be saying 3. Do you have any other outgoing edges? It will be saying no. So this is also done. I'll again go back. I'll be saying, okay, 0. Do you have any other neighbors which I need to do the DFS stuff? I will be saying, okay, yes, there is one more. Great. No worries. Do the DFS call for that as well. Okay. So now it will be saying, okay, for 4. Hey 4, are you the target node at the destination node? I'll be saying, yes, I am. So I'll be saying, okay, add it. So now this I just have one more possible pass. Oh yeah, this here, that is 4. Great. I'm adding something like this over here. 0 and 4. Now I'll be saying, okay, this is done. I'll be going back. Hey, I'm done. I'll go to 0. Is there any other node? It will say no, it is done. But also, we have messed this edge. I just looked into this thing. So what is required? Okay, there's also one more neighbor from 1 to 4. Okay, so I made call for 3. I made call for 2. I also need to make call for 4. No worries. I'll make one more call for 4 over here. Something like this. Great. So here I'll be calling the 4. I'll be saying, okay, hey 4, are you the target node that I want? It will be saying, yes, I'm the target node that you does want. Okay, add that as well into the path. That's done. Now I'll be saying, okay, that is done. I'll backtrack. That's the same thing. Backtrack from here, and then it will call for another node, something like this. So okay, this I have got one more possible path, that is 0, 1, 2, 4. 0, 1, 2. Okay. So over here, it was 0, 1. By mistake, I added the 2 over here. Till now, till this point, there's only 0, 1. So I need to write 4. So as something like 0, 1, it will call for the 4. Something like this over here. And this has to be like this. Yeah, because there's directly edge from 1. 4 is the neighbor of 1. Great. So this is the DFS, recursive DFS that I'll be doing for this particular graph. And at the end, I just have one more path, 0, 1, 4. Okay. I have one more path, that is 0, 1, 4. So these all are the possible paths that I can visit from source to result. So this is the result I have got. So let's quickly code it. So let's directly jump into the coding area and quickly code it up. So what I does have in this case? I does only graph. No worries. I does only graph. No worries. From that only I'll write all these things. Okay. I'll be requiring what? List of integer. That is what? That is path over in this case. And let's say it's an implementation class of analyst. Okay. I don't need to specify the data type again because from Java 1.7 or because of the type inference, it will just simply take whatever type it does have on the left side. And for each path, I need to store it okay as a list of paths. So I would be requiring a result array, or I could say the list of integer. That will be what result, and this will also be the implementation class of analyst. And now, what I'll be saying at the end, I'll be returning the result address have over here, and I have to make a DFS call with what all stuff. Okay, let's look into this. I'm doing DFS call from the node, current node, with the graph, with the path, with the result. Let's do that. No worries. Do the DFS call from the node. At the starting, what will be the node? That will be the source. And source is what? That is 0. And then I need to pass the graph as well, and I have to pass the path as well, and then the result in order to add path once I have one potential path with me. Great. Now I need to create a method for DFS as well in this case. So let's create it quickly. So what it will be? So private. What it's returning? It's returning nothing. It's just giving adding each potential path in the result. So it will be what? It will be void DFS asking for one node. Okay, and then whatever the graph I does have in this case from the problem statement, I need to pass that same as well, and then the list of integer for the path, and then the list of integer for the result. Great. Something like this over here. Cool. There's always thing then. So firstly, I have one node path dot add what node that current node. Now I'll check if what I'm checking if the current node is equals to graph dot length -1. That is what the target node which I does have. If it is equals to the length and is what length of the graph. If it is -1, I have found my target. Great. Something like this over here. I found my target, so I'll be saying okay, I found my target. I found one potential path. So I'll be saying okay, result dot add new array list. I need to pass a copy of this path because I need to use the same path again and again. That's what I want to say. So if you'll see, I can go from 0 to 1, from 1 to 2. I can go from 0 to 1, from 1 to 3. But in the DFS, if you say path, if you see over here, the same path is getting used afterwards as well. So 0 1, if you see, okay, 0 1, 0 1 is used over here, 0 1 is used over here, 0 1 is used over here. If I'll change this path itself, so it will change for others as well. So this should not be the case. That's why I'm passing a copy of path in the result array. That's what I'll be doing. That I'll be adding over here. So it will be different path in the result array. Are we getting it? So let's do that. I've added that. Or else, it's not the last node, it's something else. Here it's not the 4, it's something else. In that case, I need to look for all of its neighbor. All of its neighbor. That could be the potential answer. That could be the target. So let's do that. So else, look for all of its neighbor. That is end next, or I could say neighbor over here. So graph of what means I need to check. I need to check for all of its neighbors. That is the next it has for this particular node I have in this case. Okay, so it will be giving me iterating over all the neighbors which this particular node has, and then I'll be calling DFS function for that node from that node. So I'll be passing okay neighbor over here in this case, and graph has is path whatever the path I have till now, and the result whatever the result I have till now. And at the end also, I need to remove what from the path. I need to remove what whatever the last element is there. Whatever the last element I have. Because if you see here, I have 0 1 3 4. When I'm backtracking, it has only 0 1 3. When I'm backtracking, it has only 0 1. So it can be used afterwards. It is to current neighbor. It won't be using the has is. So I need to remove it for the future use cases so that another node or neighbor can use it. So I need to remove that as well. So this is the thing I'll be doing, and this is the code which I does in this case. Let's quickly run and test, check it whether it's running or not. Okay, it has been accepted. Now let's try to submit it. Cool, it has been submitted. Now I want you to understand this over here. So here, what's the time complexity I does over in this case? So over here, I does this number of nodes add as in this case. So here add as a v sorry, yeah, v number of vertices. Over here add as a v vertices, or in this case. Now what is there? I am running calling DFS function for each node. For each node, I'm running a DFS function. Time complexity is what? Time complexity will be big O of, for each vertices, I'm running a DFS. I'm calling a DFS function over here in this case, something like this. And for each in each DFS call, I'm looking for all of its neighbors. That is what all edges it does have. So that will be big of vertex plus edges in this case. And the path is what? The path will be big O vertex plus edge, and big O into the number of vertices that is in this case. So it's the if I'll figure it out at the worst case, it will be at the end it will be simply big of vertex plus edge itself. So that is the thing I wanted you to understand. So this is the I have solved it using DFS because there is the direct approach that comes to our mind. I explained you that as thought process as well. Why? Because I'll be doing the DFS depth from each node. Or let's say this is the node. From this, I need to go here for all the possible ways there are. I can go and then backtrack to look for the another possible paths that it does have. DFS plus backtracking. We can go with the BFS as well. That is the level by level. We can go with the DFS with dynamic programming as well, and also we can implement it with the topological sort because it's directed acyclic graph. So I can implement it with the topological sort as well. But in that, I need to do the DP kind of stuff as well over there in this case. So that's what I wanted you to understand and explain. So hope you liked it. See you soon. Bye bye.